There's my hello. I had to clear my voice first. I've got no special languages, but I will say hello. It's good morning for me. I'm not sure when you're watching this, but whatever. Today's lesson is a lot of learning how parabolas are graphed and sort of knowing a lot of vocabulary about these parabolas. It's really, really important vocabulary, and trust me, it'll help you a lot as you continue on in math. Axis of symmetry. Ugh. Axis of symmetry. See if I can make that a little smaller. Still awful. All right, the axis of symmetry. Axis is, you've got a car with a wheel on an axis. I don't know, I think about an axis as something that rotates around. Something rotates around, you get it. If we look at the axis of symmetry for a quadratic function or a parabola, it's a vertical line given by the graph, and to draw that vertical line, we use this equation. X equals is always a vertical line. Y equals is always a horizontal line. So x equals negative b over 2a is called the axis of symmetry. Okay, it's right here. It's a symmetrical line that the parabola, or the quadratic function, could rotate around. It's equal on this side as it is on this side. It's like a mirror image. Vertex, the next vocabulary. The vertex is the point where the graph of a quadratic function or a parabola and its axis of symmetry intersect. We can call it either, the lowest point if the parabola opens up, or the highest point if the parabola opens down. And then end behavior of a graph. It's probably the most hard to explain, not necessarily the hardest, but the hardest to explain. So given a quadratic function, the quadratic function is said to open up if a is greater than 0. That should be a pen, not a highlighter, sorry. If a is greater than 0, or open down if a is less than 0. That means when a is positive, it opens up. When a is negative, it opens down. Right, so let's look at these. Below are some examples of curves found in architecture around the world. Some of these might be represented by graphs of quadratic functions. What are the key features these curves have in common with a graph of quadratic functions? If we look, right, opens down, very cool, very wide, whole bunch of them. Okay, pretty cool. These all open down though. So the photographs of architectural features above might be closely represented by the graphs of quadratic functions. Answer the following questions based on the pictures. How would you describe the overall shape of the quadratic function? This really is your opinion, not necessarily mine. It looks like a U, right? It opens up or down. These are open down. You can draw a line of symmetry. You can also find the vertex on each one of those. What is similar or different about the overall shape of the above curves? I don't know. We've got a high point, and then the graphs open up from there. Some are very wide at the base, some are very narrow at the base. Okay, important. Many of the photographs in this activity cannot actually be modeled with a quadratic function, but rather catenary curves. These are quadratic-like and can be used for our exploration purposes as they display many of the same features, including the symmetry we are exploring in this lesson. All right, let's explore. Use the graphs of the quadratic functions, graph A and graph B, to fill the table and answer the questions in the following page. All right, let's find some points. So -1, 8, -1, +8. Gosh, we can do anything. I've got 2, -1, and 4, 3. So let's do the opposite of this one, which would be 3. Sorry, x is 0, 3. And then where are we at 1? 1, 0, 2, -1, 3, 0, and 4, 3. What's 5? 5 is not a point that we can read, so let's do, actually it is, sorry, 5, 8. Graph B, still going to start it, gosh, negative. Looks like I can read this one. We always want to find them where they cross some hatch marks, because then we can actually read it. So I'm going to do -5, comma 5. -5, comma -5, sorry. Let's see what -4 brings us. 0, -3, +3, -2, +4. Looks like -1 is a point. -1, +3, 0, 0, and 1, -5. Okay, you might pick different x's, but really you just want to pick, like I wouldn't want to pick, I don't know, things that I can't read. You know, these don't cross any, I always call them hatch marks, any marks where you can actually read whole numbers. You love to read whole numbers. Okay, you want things that cross where you can read them. Okay, big chart to fill in. All right, so if you go back to the graph, something we're looking for is the x-intercepts. I can't fit everything on the slide, so you're going to have to look at your graph and see that the x-intercept is 1, 0. The y-intercept is 3, 0. The x-intercepts, I'm sorry, those are both x-intercepts, and there's always going to be 2 when the parabola crosses the x-axis in 2 spots. Our y value is always 0 at an x-intercept. If it were a y-intercept, our x value would be 0, okay? Vertex is the highest or lowest point, right? Sign of the leading coefficient, if it opens up, it's positive. If it opens down, it's negative. Oops, down. Vertex represents a minimum or maximum. Again, if it opens up, it's a minimum. If it opens down, it's a maximum. Okay, so let's fill this out. Here I have 2, -1. This one opens up, so it's positive. Therefore, my vertex is a minimum. Points of symmetry. So this is just plug and chug. Find f of 1. Look at your graph. So f of -1 equals 8. And f of 5 also equals 8. That's a point of symmetry. Is f of 7 greater than or less than 8? So f of 7, if you look at your graph, is greater than 8. So since f of 5 is 8, and the graph is increasing on that side of the vertex, all values beyond 5 will be greater than f of 5. We're going to look at this one later. Okay, so star this one. We're going to get to another question in our classwork that'll deal with that. Let's look at B. I've got my x-intercepts, where my y value is 0, and my vertex. Here, this is an opening down parabola, so my leading coefficient is going to be negative. I know we don't know what that leading coefficient is, but we know that if it opens down, it's going to be negative, which means our vertex is going to be at a maximum. Points of symmetry, f of -1 is 3, f of -3 is also 3. If I test a point, that's all I'm doing here is testing a point. If that's -12, this is the point of symmetry for f of 2. Sorry. Yep, so f of 2 is 12, f of 6 is also 12, therefore it's a point of symmetry. I included this because I thought my handwriting would get a little messy, but I did okay. Okay, this is where things get just a little bit sticky because we've never done anything like this before. Increasing and decreasing intervals. If we look at the first graph, it looks something like that. On one, intervals of the domain, which is your x value, is the function depicted by the graph increasing. Okay, if I look at my x value, so follow along with me. If I'm moving along my x-axis, where is this increasing? If I'm moving along my x-axis, where is this decreasing? So we always read left to right. I decrease to there, and then I increase up. I'm decreasing down to the vertex. Let me get a different color. And then I'm increasing from the vertex and on. So that's how we have to notate our intervals for increasing and decreasing. This is our x values. So those are the only numbers that we're going to represent. The first one is increasing. So from the bottom, from the vertex and on, we are increasing. So I'm going to say the vertex is at x equals 2, all the way to positive infinity is where I'm increasing. Decreasing, we're going this way. So from way over here, infinity, negative infinity, all the way to the vertex, we are decreasing. So from negative infinity to the vertex, we are decreasing. Notice I put a parenthesis here and here, because I can't include the number 2. The number 2 is my vertex. If I look back up on a different blank, my vertex was 2, -1. At the number 2, I'm neither increasing nor decreasing. So from negative infinity down to 2, and from 2 to positive infinity are where my intervals are. Nowhere else. All right, let's look at the other one, the other graph. I'm going to sketch it down here in red. If I look at that other graph, let me look at it really quick. Looks like we're like that. So I'm increasing this way, and I'm decreasing that way from the vertex. There's where the vertex is. So on what intervals of the domain, so the x values are the only ones we're going to report on, is the function depicted by the graph increasing. I'm going to go from negative infinity to my vertex, which is at -2. And then I'm decreasing from that vertex all the way to infinity, because we're just looking at the x-axis. Okay? All right. What is the average rate of change of the following intervals? Average rate of change is another way to say slope. It's a fancy way to say slope, which is just change in y over change in x. If you look at your graph, if I only look at the interval x values from -1 to 0, I'm going to look at that graph and write my ordered pairs from x equals -1 to x equals 0 in red. So we have -1, 8 and 0, 3. So let's see, get rid of those for a second. I'm going to do my math. My slope, or my average rate of change, is change in y. So 8 minus 3 over change in x. -1 minus 0, which equals 8 minus 3 is 5. -1 minus 0 is -1. My average rate of change is -5 for that first interval. I'm going to get a new page. My next interval is 0 to 1. I'm going to get my ordered pairs for that first graph. I've got 0, 3, and 1, 0. So change in y is 3 minus 0 over change in x, 0 minus 1. 3 over -1 is -3. My next interval it's asking for is 0 and 3. I'm looking at my graph. 0, 3, x equals 0, y equals 3, x equals 3, y equals 0. Change in y over change in x. 3 minus 0 over 0 minus 3 is 3 over -3, -1. And the last interval it's asking for, 1, 3. Going to read my graph, finding the ordered pairs. X equals 1, y equals 0, and x equals 3, y equals 0. Change in y over change in x. Okay, those are your intervals. Now you have graph B to do. I'm going to ask you to work on those on your own to make sure you understand what's going on, and then check your answers on the next slide. So please push pause, try to finish those average rate of change for the intervals for graph B, and see if yours are the same. See if you get the right answers, okay? And this is not the right answers. Oh, I messed up. Hold on, I'll get you the right answers. All right, this would be the average rate of change for graph B. So understanding the symmetry of a quadratic function and their graphs, look at the tables and row 5 in the chart. We're going to look at the tables here. If you look at the tables which are next to the graph, in both tables, the x values increase by 1. And then the y values either increase, then decrease, or vice versa. The y values move toward the vertex value, either increasing or decreasing. They move towards, they get closer to the vertex. Or, so the y values move toward, let's see, how do I say that? The y values move toward the vertex. And then retrace symmetrically. Sorry, I needed more space, so I had to get rid of that. That's y values. To explain this better, so we know our tables, the x values all increased by 1, and the y values either increased and then decreased, or vice versa. So, for instance, with graph 1, the y values here decreased and then increased. And then the other one, the y values increased and then decreased. Okay, it's visually what I said in words. So here I say the y values move towards the vertex, so y values move towards the vertex and then retrace their steps symmetrically. Here the y values are moving towards the vertex and then retracing, same y values, the x values are changing symmetrically. All right, that one that I deleted earlier. Finding the vertex and axis of symmetry. How can we know the x-coordinate of the vertex by looking at the x-coordinates of the zeros for any pair of symmetric points? If I look, these are my x-intercepts, which we can also call the zeros. I hope you're writing this down. How can we use that to find the x value of the vertex? Watch this. I've got 1 plus 3 divided by 2 is in fact 2. So my axis of symmetry is x equals 2. I added the x values of the zeros, or the x-intercepts, together, and I divided by 2. Negative 4 plus 0, divide by 2 is negative 2. That's how it works. Understanding end behavior, looking at rows 3 and 4. What happens to the y values of the functions as the x values increase to a very large number? What about as the x values decrease to a very small number? If we look at that one, at both ends of the graph, either this one or this one, at both ends, the y values increase toward positive infinity for graph A and toward, there's an E, negative infinity for graph B. Because A opens up and B opens down. How can we know whether a graph of a quadratic function opens up or down? The sign of the leading coefficient is your best bet. If you look at the graph, you can see it. If you look at the equation, it's the sign of the leading coefficient, anything that's in front of the x squared. When it's positive, it opens up. When it's negative, it opens down. Is it possible to determine the exact intervals that a quadratic function is increasing or decreasing just by looking at the graph of the function? For the most part, yes. If you're certain if you're sure of the vertex coordinates, if you're certain of the vertex coordinate, then you can, with certainty, know the exact intervals that it's increasing or decreasing. Computing the average rate of change on an interval, which is row 7. Oh, that's funny. I copied in the one without answers. Oops. Oh, goodness, and I can't even spell. So explain why the average rate of change over the interval 1 and 3 for graph A was 0. If you look at where x equals 1 to 3, it was exactly there to there. So when we did our change in y over change in x, the y didn't change. It was 0 over whatever, which equals 0. So the function at the two endpoints of the interval are the same. The math shows that change in y, which was 0 minus 0, over change in x, which was anything. On this one, it was 1 minus 3. 0 over anything is still 0. How are finding the slope of a line and finding the average rate of change on an interval of a quadratic function similar? How are they different? You're using the same formula. The average rate of change is the same for every interval of a linear function. When you have a line, the slope is unchanged everywhere on that line. When you have a parabola, the average rate of change it changes as you move on the parabola. Can you graph a quadratic quadratic function if you don't know the vertex? Yep. Depending on what you know, you should definitely be able to. You need to know more than just the vertex. Just the vertex will not help. But you need to know more than just the vertex. Remember that we need to know at least 2 points to define a unique line. Can you identify a unique quadratic function with just 2 points? Now, if I just knew 2 points, it doesn't tell me anything. I guess it depends on the 2 points. If I knew the 2 x-intercepts, yes, I could, but if I know 2 points somewhere else on the quadratic, not enough information. If you remember a linear equation, 2 points is good. Quadratic equation, you need more than 2 points. You actually need 3. 3 distinct points, and those points cannot be linear. Cool? All right, so I need 3 points, not linear. All right, so let's have a little bit of fun. Below, you see only one side of a graph of a quadratic function. Complete the graph by plotting 3 additional points on the quadratic function. Explain how you found these 3 points. So let's start with what we have here. I've got -3, -2, 1 and 0, -3, -6, -2, -1, -1, 2, and 0, 3. So I'm going to reflect over, oops. So I have the other half of my graph. And if you look at the y values, they're exactly the same because I reflected over, right? What are the coordinates of the x-intercepts? Not as easy to figure out, but it's actually, we're going to say -1.7 and +1.7. What are the coordinates of the y-intercept? That would be 0, 3. What are the coordinates of the vertex? Also 0, 3. It's a maximum because it opens down. If we knew the equation for this curve, what would the sign of the leading coefficient be? Negative, because it opens down. Using the, if we knew the equation for this curve, what would the sign? Negative still. Verify the average rate of change for the interval -3 to -2. So I'm going to read my graph, -3, -6, and -2, -1. So change in y over change in x. Plus, plus, -5, -1, 5. Based on your answer to row 6 in the table for Exploratory Challenge 2, what interval would have an average rate of change of -5? Explain. Well, our parabola is symmetric. So from -3 to -2, our interval is +5. We can assume that from 2 to 3, our average rate of change is going to be -5 because our parabola goes up and then back down. So if we have a positive rate of change over here, we're going to have a negative rate of change over here. And that's it. Okay, work through this lesson slowly, so there's a lot of information, and you're going to have a problem very similar to some of these on your test. Okay, we're going to have to do all of our important pieces of quadratic equations, what our parabolas look like. Okay?